Gold defies expectations. What happens when it's superheated past its melting point? Prepare to have your understanding of the laws of physics challenged. Gold, when pushed to extreme temperatures, refuses to melt as expected. And this discovery could force scientists to rethink what we know about the behavior of matter under intense conditions. But here's where it gets controversial. Could it be that some solids don't have a true melting point at all? In a groundbreaking experiment, an international team of researchers subjected ultra-thin gold samples to incredibly powerful, ultra-fast laser pulses. Their goal? To see what happens when gold is heated far beyond the so-called entropy catastrophe, a theoretical boundary where a solid should lose its structure and melt. Think of the entropy catastrophe as a kind of ultimate melting point, but for situations where the usual rules of physics start to break down. Here's the twist. When gold was heated at lightning speed, it didn't melt right away. Instead, it entered a state known as superheating. In this rare phenomenon, a solid can be heated so rapidly that its atoms don't have time to rearrange into a liquid, allowing the crystal structure to persist well past its normal melting point. Imagine ice that stays solid even as you blast it with a blowtorch, just for a fleeting moment. To measure this effect, the scientists used a cutting-edge technique involving X-rays to precisely track how much energy the gold absorbed. What they found was astonishing. Gold withstood temperatures up to 19,000 Kelvin. That's about 18,700 degrees Celsius, or over 33,700 Fahrenheit, a staggering 14 times higher than the previously accepted superheating limit, before finally melting. And it remained solid for more than 2 picoseconds, a trillionth of a second, which... Blowing up gold! Scientists replace physics with 33,740 degrees superheating. Imagine this. You're holding a chunk of gold and you decide to put it to the ultimate test. What happens if you subject it to an explosion? The answer might surprise you. You'll still have gold, albeit in much smaller fragments. This precious metal has a remarkable characteristic. It's nearly indestructible. You can melt it, and once it cools, it returns to its original form. Repeat this process 1,000 times, and you'll still have the same gold bar, unscathed and unchanged. But what if we told you that gold can withstand even more extreme conditions than previously thought? Scientists have discovered that gold's resilience extends beyond our wildest imaginations. In fact, to destroy gold, you'd need to apply a level of heat that far exceeds what was once believed possible. In a recent experiment, researchers at the SLAC National Accelerator Laboratory heated gold to a staggering 14 times its melting point. This was thought to be an impossible feat, as gold melts at a temperature of 1,948 degrees Fahrenheit. The team used a laser to superheat the gold, preventing its natural expansion, and then bombarded it with ultra-bright X-rays. By analyzing the distortions in the X-ray frequencies after they collided with the gold particles, the researchers were able to determine the speed and temperature of the atoms. This experiment challenged a long-standing theory that materials like gold can only be heated to 3 times their melting point before experiencing an entropy catastrophe, essentially causing the gold to explode. However, the researchers found that gold can be superheated to a temperature 14 times its melting point, existing in a unique state between solid and liquid. This discovery suggests that gold may not have a limit to its superheating capabilities, which could have significant implications for various fields, from space exploration to nuclear chemistry and astrophysics. The superheated state of gold lasted for only a few trillionths of a second, but it was long enough to reveal fascinating insights. Theoretically, if you could prevent gold from expanding, you could heat it indefinitely. This opens up a world of possibilities for the use of gold in technology and industry. In fact, the demand for gold in these sectors has been on the rise, driven by growth in electronics and computing. Gold's utility, combined with its scarcity, makes it one of the most valuable metals on Earth. Its unique physical and chemical properties make it indispensable in numerous industrial and technological applications. The tech sector, in particular, has been increasingly utilizing gold, and its potential uses could expand even further if the physics playbook is rewritten based on this new discovery. Gold is even playing a role in unraveling the mysteries of the universe. The James Webb Space Telescope, with its ability to observe the distant universe in the infrared spectrum, relies on gold to achieve its incredible imaging capabilities. Who knows what new applications researchers may find for gold in the future? To stay updated on the latest developments in the gold and silver markets, sign up for our free commentary and analysis service. Remember, while we provide information, we do not offer personal investment advice. Your investment decisions should be made in consultation with your own advisors. By purchasing through Money Metals Exchange, you acknowledge that we are not responsible for any losses or gains resulting from your investment decisions. This website is provided as is, and we disclaim all warranties and liabilities associated with its content. Physicists superheat gold beyond sun's surface temperature and debunk 40-year-old theory. Imagine this, a piece of gold, thinner than a strand of hair, heated to a temperature hotter than the sun's surface, and it doesn't even melt. Sounds like science fiction, right? But that's exactly what a group of researchers managed to achieve, debunking a theory that has stood for over 40 years. In a groundbreaking experiment, scientists heated a solid gold sample to a staggering 19,000 Kelvin, 33,740 degrees Fahrenheit, which is more than 14 times its melting point. The feat was accomplished using a technique called superheating, and the results were published in the prestigious journal Nature. This incredible discovery not only shattered records, but also disproved a long-standing prediction about the superheating of solids. Measuring the temperature of extremely hot objects, such as warm, dense matter found in the sun's plasma, planetary cores, and fusion reactors, has always been a challenge. Until now, researchers had to rely on estimates with significant margins of error. However, this latest study has changed the game. The international team of scientists used a laser to superheat a thin slice of solid gold, only 50 nanometers thick. They then bombarded the sample with a pulse of X-rays that interacted with the gold's superheated atoms. By analyzing the change in the X-rays' frequency as they reflected off the atoms, the researchers were able to calculate the velocity and temperature of the gold atoms. Lead author Thomas White, a physicist at the University of Nevada, Reno, described the temperature achieved as extremely surprising. The team was taken aback by how hot the gold became. This is because a prevailing theory from the 1980s suggested that the superheating of solids couldn't exceed around 3 times the solid's melting temperature. This limit, known as the entropy catastrophe, was believed to be the point at which solids would spontaneously melt. Despite some earlier research indicating that rapid heating could bypass these limits, the entropy catastrophe was still considered the ultimate boundary. However, the gold sample in this study blew past that boundary, reaching a temperature more than 14 times its melting point. The researchers propose that the speed of heating played a crucial role in preventing the gold from expanding. The gold was heated to its record-breaking temperature in just 45 femtoseconds, or 45 millionths of a billionth of a second. This remarkable feat raises intriguing questions about the limits of thermodynamics and whether it's possible to overcome them by being quick enough. Sam Vinko, a physicist at the University of Oxford who was not involved in the study, commented on the implications of this research. He suggested that the findings challenge our understanding of thermodynamics, particularly the second law, which states that disorder increases over time. However, the gold atoms reached their extreme temperature before they had the chance to become disordered. The The study's biggest contribution may be the development of a method to accurately measure these high temperatures. This opens up new possibilities for investigating warm, dense matter, such as modeling the interiors of planets and fusion reactors. The researchers are now left with a question they once thought was resolved. How hot can something get before it melts? If a material is heated quickly enough, there might be no limit. This discovery has far-reaching implications for various fields, including astrophysics, material science, and energy research. It challenges our understanding of the fundamental laws of physics and opens doors to new avenues of exploration. The scientific community is buzzing with excitement and anticipation, eager to see where this research will lead us next.